Hello, today's lesson is section 6.2, heat in chemical reactions. So we're going to talk about a new term, enthalpy, and its symbol is H. It helps describe the internal energy E of a chemical reaction by accounting for the changes in pressure and volume. They picked H, I think, because basically it's heat. So delta H equals the change in internal energy plus the change in pressure and volume. Now, if you're in a laboratory setting, which most of the time lab experiments are, most of the vessels are open to the atmosphere and there's no change in pressure. So it can be rearranged as delta H equals delta E plus the pressure times just the change in volume. And this is only if we're talking about gases. But if there's no gases involved, if it's only solids and liquids, there's very little, if any, change in pressure or volume at all. So it can just be rewritten as the delta H equals delta E when there's only solids and liquids involved. We've already mentioned endothermic and exothermic reactions, but we need to talk about them more today. So endothermic reactions are those reactions that absorb heat energy. The products have a higher energy level than the reactants did. So we could rewrite this as the reactants plus heat. Since they don't give off heat, they take in the heat. So reactants plus the heat produce the products. Some characteristics of endothermic reactions. The products feel colder than the reactants. The heat is absorbed and stored in the bonds, and the delta H is positive. So notice the positive sign there because the enthalpy of the products is greater than the enthalpy of the reactants. Now, conversely, here we've got exothermic reactions. They're those reactions that release heat energy. So their products have lower energy than the starting reactants. If we wrote their equation with heat in it, it would be reactants yield products plus heat. So the heat is given off, it's released, it goes away. Characteristics of exothermic reactions. The products are hotter than the reactants. Heat is released from the bonds, and delta H is negative because the enthalpy of the products is less than the enthalpy of the reactants. If we wrote an equation and included heat in the equation, if we had an instant ice pack, so this instant ice pack has ammonium nitrate on the loose in the bag, and then there's a little bag of water inside. So when you press and squeeze and bust the water and it mixes with the ammonium nitrate, an instant endothermic reaction occurs. So the ammonium nitrate plus the water, and it absorbs the heat, yields aqueous ammonia ion and nitrate ion floating around. And it feels really, really cold. An exothermic reaction example is propane. So the combustion of propane. So this is a gas burner here. Propane, C3H8, which is a gas in the presence of oxygen, plus 5O2, also a gas, yields 3 carbon dioxides and 4 water molecules, all in the gaseous state, plus heat. So it produces heat. It gives off heat and it floats out the window. Exothermic reaction. Calorimetry. How to measure heat. Cold into hot or hot into cold, either way, the hotter item always makes the cooler item warmer. So it either heats it or it melts the cooler item, whichever way. So here is a glass of water with ice cubes in it, and here is a pan of icy cold water that is used for blanching corn. So if you boil corn to freeze, you have to rapidly cool it and stop the cooking of the corn kernels. So you want to rapidly cool it. They plunge it in icy water and then dry it off and pack it away for freezing. So that's a boiling item being dropped into a pan of icy water. So the heat flow, when we're measuring heat flow, it's measured by the change in temperature. So the final temperature minus the initial temperature is the change in temperature. So if this water, if the room temperature water was 25 degrees Celsius and you added ice cubes to it, like that, the final temperature after a small amount of time might be 5 degrees Celsius. So we would say the change in temperature was negative 20 degrees Celsius. So delta T is negative when something was warmer and it has cooled down. So if it loses heat, delta T is going to be negative. Now, if we add something hot into something cold, then let's say starting out this icy water was 0 degrees Celsius, but after that hot corn's been in there a while and it's time to get the corn out or replace the water, that temperature is 65 degrees Celsius. So 65 degrees minus 0 is 65 degrees Celsius. Delta T is positive when something goes from cold to warm. Specific heat, denoted capital C with a little sp. Different substances take different amounts of energy to heat. The specific heat of water is 4.18 joules divided by grams and degrees Celsius. So for every degree Celsius, it takes 4.18 joules per gram to heat liquid water. Water has one of the highest specific heats of any substance. And you've probably heard that people who live near the ocean, their climate, is buffered by having that giant waterway right beside them, because water does take a lot longer to heat or to cool, and it makes their climate more mild in temperature usually. So here at table 6.1 in your book gives the specific heats for several different substances. So water down here is at the bottom. Liquid water has a specific heat of 4.18. Now notice that you really, really, really have to be careful and pay attention to what state the water's in. Now they listed it as something else, but some charts might have water and then have just the gas and the solid here, but they tell us that ice is the solid, and steam is the gas here. So the specific heats for ice and steam and liquid water are all very different. So make sure you get the right phase before you write down the number. Now, generally speaking, the metals have the lower specific heats. So we've got copper, mercury, and silver, and they've got about the lowest on here. Then, now there's some exceptions. Obviously, they gave us an exception, but then the gases generally are the next ones in size for specific heats. So carbon dioxide and nitrogen and oxygen are close to 1, but ammonia gas is double, so it's not the same. It takes more heat to warm ammonia gas. To calculate heat, its symbol is lowercase q. Q is equal to mass times the specific heat times the change in temperature. So I've got the units listed underneath each one of the variables. So Q is in joules, mass is in grams, Specific heat, we said just a while ago, is joules per gram degree Celsius, and delta T is degrees Celsius. So let's do example 6.2 from your book. How much heat is lost by a piece of copper with a mass of 50 grams when it cools from 95 degrees Celsius to 20 degrees Celsius? And they give us the specific heat of copper. It's 0.39 joules per gram degree Celsius. So we copied our equation down from up above, and the mass they told us is 50 grams. Here's the specific heat, and the temperature change is, so it said it changed from 95 degrees Celsius to 20 degrees Celsius. So this one's the initial temperature, and this one is the final temperature. So we have to make sure we put them in the right order, because if we subtract them in the wrong order, we're going to get the wrong, if it's negative, the negative or positive will be wrong. Okay, so final minus initial. So 20 degrees minus 95 degrees. Now, if we subtract and if we subtract this and multiply it with these two other terms, we get negative 1,462.5 grams times joules times degrees Celsius over grams times degrees Celsius. Now let's cancel out the variables that we don't need. So grams and Celsius. So that leaves us with Q is equal to negative 1462.5 joules. And because we started out with, we had the heat capacity only has two significant digits. Our answer can only have two significant digits. So we have to round this up to negative 1,500 joules. To measure the heat, there's a tool called a calorimeter. So figure 6.5 in your book shows some different calorimeters. They try to insulate the water or whatever substance that they are putting the hot thing. They've got a thermometer to measure the changes, and they've got a stirrer of some sort to agitate and keep the whatever the liquid is to keep it moving around. So they'll measure the temperature change until the temperature equilibrates between the hot thing and the cold thing. The third one has capabilities to control the pressure or take that into account as well. It's a Baum calorimeter, but the other two are open to the air. So according to the law of conservation of energy, the heat lost plus the heat gained equals zero. So this is the premise behind using a calorimeter. Or rewritten, the heat lost is equal to the heat gained. When they put something in there that's really hot, it's going to lose its heat, and the water or whatever the medium that they're putting the hot thing into, it's going to gain heat. And then when they equilibrate, the reaction will be finished. So we'll experiment with doing that in our next lab. Delta H, the heat of reaction. So delta H is the total amount of heat liberated or absorbed between the start of a reaction to its end, where all the products are at the original temperature of the reactants. When you see a thermochemical equation, here's two examples of thermochemical equations. It's got hydrogen plus oxygen yields water plus heat, and it tells how much heat. Or it could have the hydrogen plus the oxygen yields the water, and it say delta H equals whatever amount of heat. You know it's a thermochemical equation if, number one, it does have to be a balanced equation, but it has to include the heat or in some way added to it. So it'll have an amount written in joules or kilojoules beside it. Either it will say delta H equals whatever, or it will say plus heat on one of the sides, on the reactants or the product side, and tell how much it is. Equation 6.11 may also be rewritten to express the amount of heat liberated per mole of product using fractional coefficients as necessary. So here it's been divided by 2, so it only makes 1 mole of water rather than 2. And this amount has been divided in 2 as well. So delta H here is negative 286 kilojoules. Thus, every mole of liquid water formed from its elements liberates 286 kilojoules of energy. So it gives it off. So it's an exothermic reaction. So on page 127 in your book is this giant chart with the enthalpies of formation at 25 degrees Celsius and 1 atmosphere of all these different compounds. So notice that they are compounds. In order to form these, this is the change in enthalpy to put the raw elements together and them react just like what we just saw about the hydrogen plus the oxygen yields the water. So the heat of formation, this is just the change in enthalpy. It's not the absolute amount of energy it takes. Since it's not absolute, it's relative, they're arbitrarily assigning the value of 0 for the enthalpy of all the raw elements. So if you see silver or calcium or chlorine gas, hydrogen gas, mercury liquid, nitrogen gas, oxygen gas, any of these things, any element that's just the plain element, its enthalpy of formation is going to be 0 kilojoules per mole. So the hydrogen gas plus the oxygen gas, both of them were 0, and producing the water liquid was negative 285.8 kilojoules per mole. Now here it doesn't say ice and steam. It's got water with the gas and water with the liquid. I don't think it has water with this as a solid, but pay very close attention to the state. Here's methanol. So methanol liquid and methanol gas. So I wonder how to calculate the enthalpy of formation of something that's other than water, some other substances. Here's our lovely equation. So the enthalpy equals the enthalpy of formation of the products. Delta H equals the enthalpy of formation of the products minus the enthalpy of formation of the reactants. Example 6.3. Calculate the enthalpy change for the combustion of ethanol used to power the V2 and Redstone rockets. So here we've got ethanol plus oxygen yields carbon dioxide and water. And then also we have to tell whether this reaction is exothermic or endothermic. So first of all, we've got a balanced equation. We have to add up the enthalpy of the products minus the enthalpy of formation of the reactants. So we're going to have to flip back and forth to that chart that we just looked at and make sure that we pay attention to the states, because this tells us liquid, gas, and liquid. Okay. So there are 2 moles of carbon dioxide gas. So here is its enthalpy of formation, plus 3 times the enthalpy of formation of water. So that negative 285.8. Then we're going to subtract the enthalpy of formation of ethanol. And there's only 1 mole, so we multiply by 1. And then note here, the enthalpy of formation of oxygen, that's an element, so it counts as 0. So 3 times 0. Then let's simplify our equation. So 2 times the carbon dioxide is this amount, and 3 times the water amount is this amount, and the ethanol is here. So add and subtract all these numbers together, and you should get the change in enthalpy of this reaction. Let's make sure that we've answered all the problems, everything the problem has asked for. So it is the enthalpy of the enthalpy change for the combustion of ethanol. So this balanced equation has 1 mole of ethanol. So that's important. If when we balanced it, it had been 2 or 3, we would have to divide this answer by 2 or 3 because it would need to be the change in enthalpy per mole of ethanol. And then now we look at whether this answer is positive or negative. So because it's negative, that means that it lost this amount of energy. And if something loses the energy, it gives it off. So that means that it's an exothermic reaction. So mass heat calculations. It's not always easy. It's not always convenient in actual practice to work with mole amounts of substances. For example, we might want to find out how much heat would be generated by 500 grams of ethanol rather than 1 mole of ethanol. To find the enthalpy for the change in enthalpy for 500 grams of ethanol, you would first find the delta H per mole of ethanol as demonstrated in example 6.3, which we just did. But then we would calculate the number of moles in 500 grams of ethanol using the molar mass. And then we would multiply the value of the change in enthalpy per mole of ethanol, the number we just solved, negative 1,366.7 kilojoules, by the number of moles in 500 grams of ethanol to find the answer. So let's do that. Example 6.4. How much heat energy is liberated in the combustion of 500 grams of ethanol, C2H5OH? So here's our answer from 6.3. Delta H was equal to negative 1,366.7 kilojoules per mole. Per mole. Per mole. That's important. So how many moles of ethanol are there in 500 grams of ethanol? So it's molecular weight. So I added up. There's 2 carbons, 6 hydrogens, and 1 oxygen. So all these numbers added together, 46.068 grams is the molar mass of ethanol. 1 mole of ethanol is 46.068 grams. The grams cancel out. So 500 divided by 46.068 is equal to 10.85 moles of ethanol. So now we need to multiply 10.85 moles of ethanol times our answer from 6.3. So the moles of ethanol cancel out, and we get negative 14,830 kilojoules. Because we had 4 significant digits in our question, that's how many digits we need in our answer. So we round up for this digit and have 4 significant digits. So that's the end of this section, and you'll be ready to take quiz 10 over section 6.1 and 6.2. So I will get that to you soon. We'll see when, but I'll get back with you very soon.